Two small conducting spheres which carry charges of +3 and +5 nanocoulombs, that means you're timesing by 10 to the -9. I'll place the distance of 40 millimeters apart, so you better times that by times 10 to the -3, as shown in this diagram. Then there's two theory questions. The first one is define an electric field, and that is a region of space in which a positive point charge experiences a force. The second one is, on the diagram, draw the electric field around these two small conducting spheres. So you need to do that, and because they are both positively charged, it's going to look a bit like this. So it's going to be from positive to negative, so all the arrows point away. It's radial over there, so it radiates out, and then the two interfere with each other here to cancel out the field in the middle and to create that type of a shape. Along the line joining the two small spheres, there's a point P, which is 10 millimeters from the 3 nanocoulomb charge. So the magnitude of the resultant electric field strength at P is 2,2 times 10 to the power of 5 newtons per coulomb. It's an electric field, and it's a point charge. So let's take a look at what's happening. I first need to work out the electric field at P because of the 3 nanocoulomb charge. So I'm going to say electric field is K Q R squared, 9 times 10 to the power of 9, 3 times 10 to the -9, because I'm working with the 3 nanocoulombs, and it's 10 millimeters away, so it's 0,01, and I don't forget to square that. I get 2,7 times 10 to the 5 newtons per coulomb, and that's to the right. The electric field is always from positive to negative, so it is going to be away from the positive charge. Then we are going to get an electric field which is equal to 9 times 10 to the 9, and now we're going to look at the 5 nanocoulomb, 5 times 10 to the -9, over a distance. This time it's 30 millimeters because it's 40 minus 10. Don't forget to square it, and you land up with 5 times 10 to the 4 newtons per coulomb. And this one is to the left because we are worried about what that charge is doing, so we get an electric field to the left. These are both vector quantities, so I'm able to take them and do a subtraction. I've got 5 times 10 to the power of 4 to the right, and 2,7 times 10 to the power of to the 2,7 times 10 to the power of 5 to the right. So I do a little subtraction. 2,7 times 10 to the 5 minus 5 times 10 to the 4, and I land up with a resultant electric field, which is 2,2 times 10 to the 5 to the right. This question is really quite hard because it includes your electric field knowledge and it includes your knowledge of vectors and the fact that you can get a resultant electric field. Now we've got a circuit, and that circuit has 3 resistors in it. There is also an internal resistance, and they tell me that that is 1 ohm. So let's answer the questions that are there. So I'm just going to put the 1 ohm in there. Calculate the total external resistance. I've got the 2 parallels. So it's 1 over R parallel is equal to 1 over 6 plus 1 over 4. And I land up with a lowest common denominator of 12, 5 over 12, but that's not my answer. R parallel is equal to 12 over 5, which is 2,4 ohms. R external, I'm going to have to add that and this together. So I land up, this is now 2,4. I land up with 1,6 plus 2,4. Sorry, that looks like a multiply, it's a plus. And I land up with 4 ohms externally. Determine the reading on the ammeter. My external potential difference is 8 volts. So I go I is equal to V divided by R. Total external potential difference, total external resistance, and I get 2 amps. calculate the current flowing through the 4 ohm resistor. So now I'm interested in just a parallel branch. So I am going to say that I have got a total of 2 amps. They're going to split 10 ways. 4 of the 10 ways is going to go up. 6 of the 10 ways is going to go that way, because 6 plus 4 is 10, and therefore I have a ratio of 1,2 amps. There is another way to do it. You could have put in a pretend voltmeter over here, worked out that potential difference by saying 2 amps goes into the whole parallel network, and the parallel network is 2,4. So that voltmeter would have read 4,8 volts. Then you could have said current I is equal to V divided by R, which is 4,8 divided by 4, and I land up at 1,2 amps. Finally, it wants you to calculate the EMF of the battery. So EMF is the total potential difference. So I need the total resistance first. 4 external ohms, 1 internal ohm, 5 ohms altogether. So the EMF is equal to the series current times by the total resistance, which is equal to 2 amps multiplied by 5, and I get 10 volts.